Interstellar Comet 3I/Atlas, has recently drawn intense scientific interest after researchers discovered that it was shedding water far earlier and more dramatically than expected, revealing new clues about how the essential ingredients for life may be transported across the galaxy. This comet, only the third confirmed interstellar visitor to enter our solar system, appears to have begun ejecting water like a fire hose, even before approaching the region where typical comets start to warm up and release gas. Its unusual behavior is offering astronomers an unprecedented look into the composition and evolution of objects that formed around distant stars, shedding light on the origins of organic compounds and the chemical materials that seed planets with the building blocks of life. In a new study published in the Astrophysical Journal Letters on September 30th, researchers analyzed data from the Neil Gehrels Swift Observatory and reported the first clear evidence that 3I/Atlas was actively releasing water at an exceptional distance from the Sun, nearly 3 times farther from it than Earth. At this distance, water ice on most comets in our solar system remains frozen solid, so the detection of water vapor coming from an interstellar object at such a location was both unexpected and scientifically thrilling. Study co-author Dennis Bodwitz of Auburn University described the detection as reading a note from another planetary system, emphasizing that water, and by extension, the molecular ingredients necessary for life, may be common throughout the universe rather than unique to our solar neighborhood. The importance of detecting OH, the ultraviolet byproduct created when sunlight breaks apart water molecules, cannot be overstated. This signature confirmed that the comet was indeed releasing water, even though it remained at a distance where solar heating should not have been strong enough to vaporize ice. Calculations revealed that the comet was ejecting an astonishing 88 pounds, or roughly 40 kilograms, of water every second. This enormous output is comparable to the pressure of a fire hose running at maximum strength, painting a vivid picture of the immense forces at work inside the comet's nucleus. The early and intense sublimation suggests that 3I/Atlas contains particularly volatile materials, or that its surface layers include fine grains of ice that react rapidly to even weak solar energy. Since its initial discovery in July, 3I/Atlas has been under constant observation from multiple ground-based and space-based telescopes. As an interstellar comet, meaning it originated outside our solar system and is merely passing through, every detail about it has become a valuable piece of a much larger scientific puzzle. Researchers believe it is traveling through our solar system at speeds exceeding 130,000 miles per hour, 210,000 kilometers per hour, following a nearly straight, flat trajectory that is characteristic of objects not gravitationally bound to the Sun. Its extreme velocity shows that it has been roaming through interstellar space for millions, perhaps billions of years, before being nudged onto a path that eventually intersected with our solar neighborhood. One of the most remarkable aspects of 3I/Atlas is its size. Based on Hubble Space Telescope measurements, astronomers estimate its maximum width to be approximately 3.5 miles, 5.6 kilometers. If confirmed, this would make 3I/Atlas the largest interstellar object ever recorded, dwarfing the sizes estimated for the previous visitors, 1I/Oumuamua and 2I/Borisov. Moreover, emerging research suggests that 3I/Atlas could also be the oldest comet ever detected. One study estimates it may be as much as 3 billion years older than our solar system, meaning that this object likely formed around a star that predates the Sun by an immense span of cosmic time. If accurate, the comet represents a surviving fragment from an ancient planetary system that collapsed long before our own Sun ignited. For their most recent study, scientists used data collected in July and August using the Swift Observatory's ultraviolet and optical telescope. This allowed them to track the hydroxyl signal produced as water molecules were broken apart by solar radiation. Because the comet was so far from the Sun, traditional sources of water activity seemed unlikely. Instead, researchers proposed that the ultraviolet signal was coming from small icy grains on the comet's nucleus. These grains likely vaporized into gas as the comet experienced minimal but still sufficient heating from sunlight. The fact that water activity was triggered at such a distance suggests that 3I/Atlas carries a surface layer rich in extremely fine or loosely bound ice, possibly accumulated over long periods of drifting through cold interstellar space. This unique characteristic sets it apart from most comets found within our own solar system, which usually do not exhibit strong water-driven activity until they are much closer to the Sun. 3I/Atlas marks only the third time scientists have had the opportunity to study an interstellar comet in detail. The first such object, the elongated and controversial 1I/Oumuamua, baffled scientists with its dry composition and lack of visible comet-like activity, leading to debates about its nature and origin. The second, 2I/Borisov, was more typical of a comet, but unusually rich in carbon monoxide, indicating that it had formed in an extremely cold region of its home system. Now 3I/Atlas has revealed a completely different profile, shedding water at unprecedented distances. These three interstellar objects, each distinct from the others, collectively suggest that the universe hosts a wide variety of planetary systems with diverse chemical environments, temperatures, and histories. Their differences highlight that comets formed around other stars may not resemble those in our solar system, offering a broader perspective on how planets and organic materials form across the galaxy. Let author Zishi Xing emphasize that each interstellar comet observed so far has challenged scientific expectations. 1I/Oumuamua lacked the typical volatiles of a comet. 2I/Borisov carried clues of a frigid birthplace rich in carbon monoxide. Now 3I/Atlas has introduced yet another surprise by displaying abundant water activity far from the Sun. These variations reveal that interstellar comets preserve the chemical fingerprints of their original environments, essentially serving as time capsules of ancient planetary formation processes. Because comets are formed from the leftover materials of star and planet creation, studying them provides rare insights into the conditions under which those systems arose. Interstellar comets are therefore priceless scientific messengers, giving researchers a chance to directly sample the materials that exist beyond our solar system. The discovery that 3I/Atlas is shedding water at great distances also carries important implications for understanding how life's essential components may travel between star systems. Water is a fundamental ingredient for life as we know it, and finding it in an object originating from another planetary system supports the idea that hydrated materials may be widespread across the galaxy. If water-bearing interstellar comets regularly travel from one star system to another, they could play a significant role in distributing ice, organics, and even prebiotic chemicals across vast cosmic distances. This notion connects to long-standing scientific theories, such as panspermia, which propose that life's basic components might be transferred between worlds or star systems by natural cosmic processes. While the detection of water on 3I/Atlas does not confirm such theories, it strengthens the concept that life's raw materials are not confined to one location, but may instead be shared throughout the galaxy. As scientists continue to analyze the data captured from 3I/Atlas, more answers, and inevitably more questions, will emerge. The study of this interstellar comet is still in its early stages, and researchers are eager to explore its chemical composition, structural properties, and thermal behavior in greater depth. With advances in telescope technology, including the capabilities of the James Webb Space Telescope, astronomers hope to gain even clearer insights into the materials that make up interstellar objects. Each new discovery enriches our understanding of how star systems evolve, how comets behave under different cosmic conditions, and how widespread the building blocks of life may truly be in the universe. The continuing investigation of 3I/Atlas promises to reveal more about the mysterious origins of this ancient traveler and deepen our understanding of the cosmic pathways that connect star systems across unfathomable distances.